This is the third and last block of this tutorial and is concerned with the integration. And here I unfortunately cannot give you an algorithm or something where you can just plug in your variables and the algorithm tells you how best to integrate your monitor. So what I can give you here is more or less an anecdote of our experience when integrating a monitor into a CPS. And I can tell you the lessons we learned so you can draw conclusions from that. In this part, I also want to tell you a bit about the postmodern analysis in addition to that. So for the process of integrating our monitor into a system, our target was the DLR Super Artis. DLR is the German Aerospace Center, and the Super Artis is the aircraft I showed you throughout the entire presentation here in this little circle. And you can see the Super Artis in action in the background here. And this picture here was actually taken during the test flight, which was a week ago. So here we were able to actually integrate the monitor into the system and let it fly. Now this test flight was scheduled for November 2019. However, due to bad weather, it had to be delayed until early 2020, and there was this, you might have heard of it, there was a little pandemic raging over the world. So we had to delay this group activity of a test flight a little further, but last week it actually worked. Now, in terms of size, you can see a comparison here. So the system is not really gigantic, but it's still large enough so you really don't want to have it fall on your head. The test flight was mainly used to test this little thing below the aircraft, which is an optical navigation system developed by the DLR. And we kind of piggybacked onto this test flight and put our monitor on there and see what happens. Now, the main challenge for this integration was the following. The Super Artis was already fully developed. So adding our monitor was more or less an afterthought because the system was already there, we just added a new component. And this especially entails that the system architecture was already fully functional and there was very little leeway on which we could integrate our monitor. We couldn't really change much of it. We were pretty much lucky because what we could do at the end was just add our monitor behind the logger. So the whole system architecture looks like this. We have an array of different sensors like cameras, GNSS and all of that. And they all communicate over a common bus. And this bus delivers the information to the position estimation and to the logger, and the result of the position estimation also goes to the logger. The logger then takes all of this data and writes it on a hard disk. Now with our modification, it also sends all of this data to the monitor and we can use it for our analysis. This, however, is not always possible. So when trying to integrate the monitor here, there's one key question, namely, do you want to do snooping or do you want to have direct messages for the monitor? Snooping means you connect the monitor to the bus and just read everything that is there and use this information. This is a decent solution, but sometimes it's not possible, especially if messages on the bus are encrypted. So here you need to resort to something else. And also sometimes it's just not possible to connect the monitor to a common and central bus. So instead you can opt for using direct messages. So some component sends messages to the monitor. However, this is always not always possible, especially when the system architecture is already fully developed. Then the bus maybe is already utilized to an extent that we cannot add new messages for the monitoring purposes. So once again, if you start early and the system architecture is not fully developed, you can add the monitor there and find a better solution where all of the components are happy. But adding monitor as an afterthought is pretty much a hassle here. When deciding to send direct messages, then another major problem is that the component that prepares these messages and sends them to the monitor needs to have resources available. In our case here, the logger was severely underutilized, so there was a lot of resources available to just send the messages to the monitor with no further problem. But this, once again, is not always the case. So after deploying the monitor somewhere, you have to find specifications you want to monitor. In our case, we had two major categories of specifications. The first one is sensor validation and cross-validation. Here in particular, we had a look at the GNSS and the IMU module. They just offer themselves for cross-validation because they can both be used to estimate a position. And the more involved kind of specifications we had were geofencing. And geofencing means that you have a predetermined set area where your aircraft is allowed to fly, and you may not leave this area. So what you can see on this picture here is the yellow part is the trajectory of the aircraft, and the orange lines are the geofence. And the idea is that the aircraft may not leave this orange area. You can see this happens here quite often, and of course during the actual flight the geofence was much larger, but we wanted to see whether the monitor is able to detect these intersections, so we had an artificial geofence. Now, in order to detect geofence violations, what we have to do is we take the current position of the aircraft here and the last position, which is the little less opaque version of the aircraft here, and we compute a vector that goes through these 2 points. And this vector is then checked against every single face of the geofence, whether there is an intersection or not. And if you recall what I said about the hardware monitoring, there we tried to find the perfect specification for the parallel execution, where we can see that the parallel execution really has an impact. There we used some command response property. But the idea of the kind of specification is really similar, because we have some kind of common data. In this case, this is the green line here, the trajectory vector. And we want to check several different things, and all of these checks are independent of each other. In this case, we want to check an intersection, check for an intersection with any of the geofence's faces. And all of these checks are independent of each other and still arithmetically challenging. So this is pretty much the perfect scenario where we can see that the hardware monitoring really shines. And as a little bonus on top of that, geofencing is a really important problem, a practical problem that has a high relevance because it's used pretty much everywhere in avionics. Now, we had our specifications and we compiled them to VHDL and synthesized them on our FPGA. And what we can see here is that the memory consumption, so the number of flip-flops we had here, was really low. It ranged between 3% and 5% of the available memory. So this was no concern at all. The lookup tables, however, are used to express the logic of the monitor. And here we needed a lot of them. So 71% for the geofence specification. And the more faces the geofence has, the more lookup tables we would need. So there was not too much space to add new additional faces here. What we can see in the power consumption is that when idle, the monitor needed 150 milliwatts. And this is pretty much nothing for a system like the one we had at hand. So this was completely negligible. And even under peak pressure, the power consumption was around 2 watts, which is still not much. It didn't bother the system at all. So that's pretty neat. Okay, so what we can say as a conclusion for our test flight is it was a huge success. We could see that especially the geofence specification was the perfect kind of specification for our system. And we can see that the parallelization really could really shine here. We could also see that the memory consumption was low, and the energy consumption in particular was also, the power consumption was also sufficiently low to warrant the integration of the monitor. So lastly, I want to talk a little bit about a postmortem analysis. And the postmortem analysis is conducted after the termination of the flight, especially if the flight failed for some reason or the mission failed for some reason. In this case, we want to see what happened and where something went wrong. Now, in the ideal scenario, the postmortem analysis is relatively simple because we have one component and this component has access to all relevant information and dumps every single point of data we obtain during the flight into a log file. Afterwards, we take the log file and do any analysis we want to do. This, however, is not always possible for several different reasons. For example, the throughput might not be sufficiently large, so we can really dump everything into a hard disk, or the logging module does not have access to all values. So there's a couple of different reasons why this might not be possible. And in general, it isn't. Now, this is where postmodern analysis becomes interesting, because to prepare the postmodern analysis, we have to log every relevant point of information available to us. So that means that the logger has to refine and filter data. So in summary, what we have is we have a component that needs access to critical data and refines this data, filters this data to get information that is interesting for the analysis of the system after the fact. And this is remarkably similar to the idea of the monitor, because the monitor also needs access to every critical point of data, and it naturally already refines and filters data. So why do the whole thing twice? If we have already a well-integrated monitor, we can just use the output of the monitor, dump this into a file and use it instead. So here monitoring can be extremely beneficial. However, this requires that our monitor has some quantitative output and better be stream-based, because if we just have one Boolean output at the end, this is not particularly helpful for the analysis. Okay, so that's all I wanted to say about the postmodern analysis. So let me conclude my tutorial. The main takeaway message of this tutorial is that when developing the monitor, you have to take the CPS into account, and when developing the CPS, you have to take the monitor into account. And this can be seen in several points during my talk. So in the first block, we talked about a specification. And when deciding on which specification language to use, you have to take into account what kind of properties do we want to monitor, in what kind of setting will the monitor be executed. And depending on this, you have to pick a different language. So here, we cannot just say, okay, we have some language and we want to integrate it somewhere. It depends on what we actually want to achieve. Then in the second block, we talked about the compilation of the specification onto hardware or software. Once again, what you want to have depends on the system. It depends on the platform where your monitor is going to run on. So you cannot just say we have one compilation and this compilation is perfect and we have to make it work. No, you have to see in what kind of environment are we working and what is the perfect solution for the system as a whole. And lastly, in the integration block, it is most evident why there is a co-development between monitor and cyber-physical system, because the CPS has to prepare a spot for the monitor where it can really work. And only in this case, the monitor can be beneficial for the CPS as a whole. So if I want to put all of this into one sentence, then I would say, for a monitor to show its full potential, it needs to be co-developed with the CPS. None of these two systems should be developed in isolation, and a monitor should certainly not be added as an afterthought to a fully functional system. I hope you could learn something in this tutorial, and if you have any questions, I'm happy to take them, and also if you have some feedback, please let me know. Thank you.